them, and the other competing systems would also. And whether your graphing calculators have them, I really don't know. It would have to be a high-end one, I think. I'm not sure about that. So the three are called the midpoint rule, the trapezoidal rule, and Simpson's rule. And that's what I want to talk about today. That's the section 8.6 or 8.7 in your chapter, depending on which edition of the book you have. So first of all, we get the trapezoidal formula, which should not surprise anybody from considering the area of the geometric figure that looks like this with two parallel sides that we call a trapezoid. And so the sides, the spacing between the parallel sides will be h when we get down here a ways. So imagine a setup like this. You can certainly get the exact formula for the area because you're thinking of it that the edge up here is a line that's possibly slanting with slope m and that intersects the y-axis at some value b. And so the area then in green would be the integral from this side to that side, the top minus the bottom, which I'm taking on the x-axis, so it's y equals 0. And you integrate as in Math 170 and put in your limits, and you end up down here. You have your upper limit values minus the lower limit, and then you rearrange so you have the squares together with the common factor m over 2, and then you have the first powers together with common factor b, and use h as your spacing between the parallel sides. And so that's the x2 minus x1, and then suppose you use y1 as your height to the line at x1, and y2 is the height to the slanting line at x2. So then we could say that the area in here, the area that would be in green, is equal to doing some work with this. You see you have a difference of squares, so you can factor that, and then this factor is the same as h, and then you have h over here also, as I indicated with my arrows. So then I have h here and there as a common factor, and then I have the m over 2 times the sum of the base points. The values like x1 and x2, where you're measuring the height to your upper curve, are called base points because they're at the base of the figure, obviously. And so you have the slope times then the sum of the base points over 2 and b. So then what you can do is get a common denominator of 2. So multiply and divide over here by 2 and then factor that out. So now you have half your spacing of your base points. mx2 plus mx1 plus 2b. Use one of the b's with each of these. So put one of them with the mx1 and the other one with the mx2, and then you can call that y1 and you can call that y2, which would be the y values for your top line. Remember that we're talking about a trapezoid, so this top is a line as opposed to some other sort of curve. So with those assumptions, all of this works. So finally, then, your formula, your exact formula for the area of the trapezoid is h over 2, y1 plus y2, or like this. So it's the width, or spacing between the base points, times the average height. Okay, so a person could have said, well, you know from geometry that that's the formula for the area of the trapezoid. That's true. Or anyway, for whatever it's worth, you see how you prove it using calculus. And so then getting on with where we're going, which is using trapezoids to give you an approximation to the area where there is some top curve f of x, not necessarily a line. We can think about something like this picture. You have a top curve here, f of x. And where you would really use this is in a case where you don't have a way to get an exact closed form antiderivative. Something like sine x divided by x. None of the tricks that we've studied for getting antiderivatives will give you one for sine x divided by x. You would think maybe you could do it by parts, but you try it, you won't get there. What we eventually get to in mathematics after we run through our encyclopedia, if you will, of functions for which the integration will give you another function that we know, is that if you want the area between some new function for which you don't know an antiderivative, and the book doesn't, and Maple doesn't, and so on, you have to do something like this, and then use, if it's important enough, you can use either the integrals that you get by numerical approximations, or use infinite series, which we will study in chapter 10. One of the other of these methods allows you to get values that you could put in a calculator, or in times past actually print as in a table. And such work had to be done, for example, with the functions that you use in statistics for the area under the bell curve that was first studied by Gauss. And Gauss first did the work of getting values for the integral under that curve, which you use for probabilities if you're in a statistics class. So that's an example of something that had to be tabulated, by which you mean you have to do something like what we're in the process of learning to do here, which gets you values for the area under the curve from some starting point to some convenient stopping point, and then you calculate that value, and that you can put in the table as the value of your function between one point and another, which is, after all, what people did with the trig functions and the logarithm. We'll talk about how you could use the kind of thing we're doing today to get values of logarithms, which is one of the ways that people can go about tabulating the logarithm. You think of it, well, I have a calculator and it tells me, yes, and before that there were tables in the back of the book that would tell you, but somebody had to get those values, you see. And the somebodies worked very hard doing it all by hand. So anyway, back to here. You could think of putting a trapezoid there, the blue one. Maybe you can see there's a slanting blue line. The orange one here, you can really see remember, if it's a trapezoid, the top is a line. So it may miss the actual curve by a substantial amount. Then there's another trapezoid here, and another one here, and another one there. It's just kind of a happen so that in this picture, the blue ones are closer to the curve than the orange ones. So they also notice that your top of your trapezoid might be above your curve. You see, if it's concave up, and it can be below the curve if it's concave down. So your trapezoidal area may be too big or it may be too small for any one of the pieces that you use. So then you have base points. Say, in this picture there are 6 of them, and so then with my trapezoidal approximate area, h over 2, the sum of the heights to the top curve, I have the common factor of h over 2 for all of them, and then I have the sum of the heights for the blue one, and then the sum of the heights for the orange one, and then the blue, and then the orange, and then the blue. We're honoring the semi-professional football team again, of course. And notice that at the interior base points, x1 through x4, the height appears twice. See, it's blue from that one and orange from that one, and again and again. So if your spacing then is the length of the interval divided by the number of slices, b minus a over n, so that that's a common factor. There are n slices and there are n plus 1 base points. Slices are the trapezoids, of course. And so our trapezoidal formula really then is the h over 2, the height at the first base point, then twice the height for all the interior ones added together, and then the height at the right hand or last base point. If you assume over this interval that your second derivative is bounded by some number that I represent with capital M, and then if you say the error with a subscript t for trapezoid is the difference between the computed value using this formula and the true area under the curve, which would be the definite integral, which you might or might not be able to get depending on what this function is, then the theoretical error bound, which we're not going to prove, but which you would prove if you were taking a class in what's called numerical analysis. is the bound for the interval on the magnitude of your second derivative of the top curve times the length of the interval, a to b, so it's b minus a, over 12 times the squared spacing. Now remember, if you're doing serious work where you really care about the answer, you're going to use a comparatively small spacing, maybe a tenth or something like that, and you're going to do it with a computer or at least a good calculator. And so this is normally going to be the square of a small number. So even if h were a tenth, which is a pretty big spacing really, this is 100. So then so long as m is a reasonable number in size and the length of the interval is reasonable in size, you have a factor, if h is a tenth, of 1 in 1200 here. So that's going to cut the theoretical maximum error down to something that's small, can be made basically as small as you like by taking a small enough step size spacing, space between the base points. And so the standard definition of error when you do a numerical computation like this is computed minus true. So of course you could also say the true value is the computed minus the error and so on. And you have to define, you see your error can be that your computed value is too small or that it's too big, and so you have to define which way you're calling positive and which you call negative. And that's really whose book are you in? And it's not really the point for us, except that you do such a thing. So there is also the midpoint rule and the error in the midpoint rule. So pictures with midpoint rule, for example, you could look over here, you could look at y equal x squared, and of course there's no reason to do the area under x squared numerically, because you can do the integral. It's x cubed over 3, and between 0 and 1 it's 1/3, but just as a demonstration. So you see, it's a curve that's concave up for its the whole interval that we're going to study. And of course you can get the exact value, which I said. And you can see that if you do the trapezoidal rule with these base points, you'll get 22 over 64, and the true area 1/3 is 21 over 63, so this overestimates. You can see that it does, because you see that for all of the 4 trapezoids, your slanting top in green is above the curve. That's the case where it's increasing and concave up. The midpoint rule would be like this picture. You have the same base points, 0, 1/4, 1/2, 3/4, and 1. Then using those, you get the marks that are in black here, and those may be a little heavier. Then you take the midpoints between these in pairs. So if that's 0 and that's a quarter, the midpoint's an eighth, right? Even this early in the morning. And between a quarter and a half, the midpoint's 3/8, and so on. So the midpoint rule is you take the height to your curve at the midpoint after you've set up the original base points, and then use the rectangles, where the height of the rectangle is measured at the midpoint, height of the curve, of course. So for this example, x squared, this is x squared also. Then your height will be the midpoint value squared. And then the widths are, in this case, 1/4 for all the rectangles. And if you do that, you'll get 21/64. Remember, 21/63, which is a third, is your actual integral. And the 22/64 was your trapezoidal rule. And so what you have, when it's concave up and increasing like this, is that the true value, the integral, is between what the area computed by the midpoint rule gives you and what the area computed by the trapezoidal rule gives you. And these are not terribly far off, but when you have a curve like this, these are not exact, whereas, of course, the integral is, if you can do it. Your trapezoidal rule, back to it, the error, wherever I had that, where you see it depends on the maximum value that your second derivative can take. So that means if your top is linear, the first derivative then is constant, and the second derivative and higher would be 0. So the second derivative 0, when your top curve is a straight line, means the trapezoidal rule is exact for a linear top curve, and then in error if it's quadratic or higher. So there is a more precise rule with a smaller error called Simpson's rule over there under the clock that we'll talk about in a minute. But notice here that for x squared, if you used x1 as 0 and x4 as 1, and your spacing is 1/4, your trapezoidal rule area, which is how you get the numbers I've been talking about, a sub t is your spacing, your h, over 2. Then, as I said, the left-hand edge of your left-hand, or your leftmost trapezoid put in once, then twice the heights for all the interior base points, and then the height once for the right-hand side of the right-hand trapezoid. And you call these numbers, the 2's and the 1's, the weighting factors. That's spelled this way, this kind of weight. I was just looking at my writing and thinking what a strange language this is, because you have the same pairs of letters, the EI. This is weight, but this is height, right? Same spelling, don't say it the same way. What sense does this language make? Anyhow, for this example, then you see your y being your square, you have at your leftmost base point your 0 over 4 square, 1 over 4 square, 2 over 4 square, 3 over 4 square, 4 over 4 square. Notice you can get patterns to these because you have the common denominator here, and then you have the sum of the squares of the natural numbers. Most of these, when you really are doing one of the problems, you'll have a pattern sort of thing like this. And if you look at what Maple does, which we'll do in a minute, you'll see that they're quick to recognize that and write the thing with the summation symbols. So anyway, if you work this out with these numbers, your trapezoidal area, if you look at the sum of squares here, you notice your denominator is 8 times 16, and then you have 1 plus 4 plus 9 plus 16. Anyway, those numbers will add up to the 44, and then you can rewrite that with a common denominator of 64 to make comparisons with your exact area, with which you do with an integral, or your computation, which is similar to this using the midpoint rule down here. So with your midpoint rule, your midpoints being an 1/8 and 3/8 and 5/8 and 7/8, as in my picture here, you see in the numerators you have 1 square, 3 square, 5 square, and 7 square. Denominator, you have 8 square, which is 64, all times the common width, which is 1/4. And so that gives you 21 over 64 as compared to 22 over 64. And your true area is in between. You could, if you have a calculator, you could get the decimal values for 21 over 64 and for 22 over 64 and compare with a third, and I think you'll see that's true. Okay, some people have arrived who didn't get the first handout. Did you get the one that said a little bit of the Wikipedia article about Simpson, which Simpson was a person who had an interesting life, so. Simpson's rule is a very accurate formula. Usually, anything you say related to numerical analysis, you have to say usually, because one thing that is true with numerical analysis is that any procedure, such as the trapezoidal rule, midpoint rule, Simpson's rule, or other things that you get into, say, in solving differential equations, for example, you can find a situation where your procedure actually fails to give you good values as far as being accurate, even though most of the time it works just fine. So that's why if anybody's doing anything that's truly important, you need to consult with somebody that's pretty expert on numerical methods. Well, we start with what people call the prismoidal formula. And a prismoid is a geometric figure like this with the two parallel sides, like the trapezoid, but with a curvilinear top instead of a slanting line top. And again, a spacing between the parallel sides, which for Simpson's rule we take as 2h. You'll see why as we wade through this. So it leads to Simpson's rule. In fact, the prismoidal formula that we will get here is the 3-point Simpson rule. And then what you do, you get a formula for the area of a figure like this, which is exact, actually, if this is quadratic, and my proof here is for the quadratic case, you see the general parabola. And actually, it's true if this top curve is cubic, but it's more writing, and so I'll spare you. But it is actually exact for a cubic top. Then if you had polynomial that's higher degree than cubic, there'd be some error of approximation, but you, with something that's exact for quadratic and cubic both, you'll find that the values are very good as a rule. The error depends on the maximum fourth derivative. So where Simpson's rule would lead you astray would be if your top curve is something for which the fourth derivative of the top curve is a very wild graph and would take really extreme values. And it's possible to dream such a thing up, but it's not likely that you'd ever meet such a thing in real life. Anyway, the theoretical error for the Simpson rule obeys this maximum possible value for your fourth derivative over your interval times the length of the interval over which you're doing your calculation. Fourth power of the spacing over 180. So here again, if your spacing is a comparatively small number, like a tenth, then you have 1 over 10 to the fourth times 180, which is a pretty big denominator. So you're going to have a really small theoretical maximum error unless your fourth derivative is just way, way out of hand, or you have an extremely long interval, and these are not likely situations. So if your M is roughly the same for the Simpson rule as it would be for if you were using the trapezoidal or the midpoint rule, if you have something where the fourth derivative is not a whole lot different in magnitude from the second derivative, then you see with a spacing of 1/10, if you were comparing h4 over 180 with h square over 12, which is what you get from the trapezoidal rule, the ratio of theoretical maximum errors, Simpson to trapezoidal, would be h square over 15. So if h is a tenth, the comparative factor is 1 in 1,500. Well, where's a situation where your fourth and second derivatives are approximately the same? Well, sine and cosine, because you start with sine or cosine, and you start doing derivatives, and all you ever get is sine or cosine back. So second derivative is say you started with sine, second derivative is sine, fourth derivative is sine, right? And so on. And so that's a situation where Simpson's rule for a spacing of 1/10 is more accurate by approximately a factor of 1,500. So it's really usually a 5-point or at least a 7-point Simpson rule is a very accurate formula. It's a rule. So we look at the prismoidal formula then, which is, as I said, exact quadratic and cubic curves. So here's our derivation. We have our curve here, and we take the center point of the 3 base points at 0, which I'll call x1, and then minus h, which I'll call x0, and h to the right, which I'll call x2. So this is equal spacing in here. And then your points up here on your curve, I'm using the curve here as parabolic with A, B, and C to be determined. And so with this formula, we'd have y0, y1, y2 corresponding to substituting x0, x1, or x2. So I substitute in to this formula. And you see the x0 is minus h. So I put in minus h and square. I put in minus h and I put in the c. And this is plus and that's minus, so I simplify. I do the same at the right-hand one. And you notice that these terms are identical, so are those, and these are opposite sign. So if you add it together, you'd get 2 of these and 2 of those, and that's gone. And then in the center, at using x as 0, I have just the c. Now, where Simpson was inspired is what I would say. This is where people get the flash that you call genius, I think. If you somehow or other decide to look at this expression, so the y0, for which you have this value, the y2 for which you have this value, and 4 times the y1 for which your value is c. So you take the green, the red, and 4 times the blue here, which you see I've done, and add it up, you get 2a h squared plus 6c. And your natural reaction to that is, so what? Well, here's what. If you do the definite integral, which is your exact area, between minus h and h for this expression, and work through that as you would as a Math 170 student, put in your limits, you get 2a h cubed plus 6ch over 3, and then you see you can factor the h and the 3, and now what's here is the same as this. So what that lets you say is that the exact area for the prismoid is 1/3 the spacing times this expression related to the y values, the heights to your curve, y0, 4y1, y2. So that gives you this formula, which is exact if your top curve is parabolic and you have the heights to the top curve at the 3 places that are spaced in this symmetric way. So you can have in other words, you can assume your top curve is parabolic of some sort, or cubic, because it's actually true for cubic, although I haven't proved it. You can measure your data at 3 separate places, spaced in this way, and you can then use the spacing over 3 times what you get out of your measurements as the exact area under the curve. And so that's why this is so important, and it's accurate because it's accurate for cubic as well as. So if you take the same 5 base points that we used in our trapezoidal and midpoint rules, you see you have 2 prismoids that you're putting together. You have the blue one, where your base points are 0, 1/4, and 1/2, and then you have the orange one, where your base points are 1/2 and 3/4 and 1. This is the equivalent to what we did here with the trapezoids, the blue and the orange. Here, with the trapezoidal rule, I had 5 of them. With the prismoidal formula, for the same base points and the same curve, I would just have 2 of these prismoids, because they take 3 points at a time. And in other words, these are bigger bites of food, but not as many bites, if you want to look at it that way. So then I've identified with my colors my 0, 1/4, and so you see the 1/2 or 2/4 is in there twice. Once it's blue and once it's orange, and then that's in once, and so on. So if you use your formula, your H is going to be the 1/4, and the 3 comes as part of the formula. And you get this 3 in here when you do this integration, so on. Then you have your base point square for your height, so the 0/4 square. Then you have 4, because that's this 4, times the square at the next base point. Then you have the blue, the 3rd base point in once, and then you have it again once more as an orange base point, the left-hand one for this prismoid, and then you have 4 times the center one, because that's what the formula does, and then you have the base point square for the height at the right. So you notice then there is this pattern in a 5-point Simpson rule, the spacing over 3, then your height, weight factor once, your height, next point over, weight factor 4 times, then weighting factor 2, which is the right hand from the first prismoid and the left hand from the second, then 4, and then finally 1. So with the Simpson rule, however many base points there are, the weighting factors are 1, 4, 2, 4, alternating that way, and ending up with a weighting factor of 1. And it's always going to be an odd number of base points and an even number, you see, of divisions for each prismoid like this. So it's either 3-point Simpson rule, which is this, the prismoidal formula, or next is a 5-point Simpson rule, which is that, and then there'd be a 7 and a 9 and so on. But usually you're working against yourself with Simpson's rule to take too many base points, because you have an accurate formula, and what you do is you introduce round-off error by doing more and more and more calculating, which you do as you add more base points. So trying to get a smaller and smaller interval can be self-defeating, because it's just going to be more machine grinding and more chance of round-off error, which can be a serious issue if you're talking about serious computations. So anyway, you grind this through, and you see you come out exactly with 1/3, which of course is your definite integral. So you can see it's exact for this case. So I've written my general Simpson rule here and pointed out what I just said. The 3-point one is the prismoidal formula. So let's look at some other things here. I have a handout on comparison of midpoint and trapezoidal and Simpson rule errors. What I have on this is what I have written one place or another on the board, that you notice that the theoretical maximum error for the trapezoidal rule divides by 12, whereas for the midpoint rule it divides by 24, where the numerators are the same. And so the midpoint rule actually has a theoretical maximum error that's only half as much as the trapezoidal rule. And you can kind of see that, I think, if you, of course, pictures are not a proof. I'm not trying to prove these, but if you look at your pictures for x squared, where, as I said maybe about an hour ago, when it's concave up and increasing like this, the tops of the trapezoids are above the curve, so it's bound to estimate high. If you look correspondingly at the midpoint rule, rectangles, you see there's an averaging effect in that, for example, this rectangle, where you can see it easier, you have some area that's actually not under the original curve. In other words, this piece, this right in here is too much, but on the other hand, you're missing this. So it isn't exact when your top curve is not aligned, because as you can see, where you have an extra here, it isn't as much as what you're short up in here. You can see this is, in my picture, a bigger area than that, but nevertheless, you do have kind of an averaging effect with the rectangles. And so in that way, it's believable, I think, that this actually might end up more accurate than this, because here you don't have any compensation for the fact that really all four of these trapezoids are too big. However, they're not terribly too big, and by reducing your spacing, you have less and less error of too big, but it's always on the too big side. And this is kind of, well, is it really too big, or is it just about balanced out? if you look down in these, you'd think it's about balanced out. So that's intuitively what you have. Now, on the other hand, if you have something that's decreasing and concave down, your situation is the opposite, because you see here, this is 1 minus x squared for your top curve, and looks as you can see in the picture. And you can do the integral and get exactly 2/3. And you can also put in the 4 trapezoids, and you can see they're all too small. And so you expect that if you did the trapezoidal formula for these base points and this function, that what you'd get would be something less than 2/3. And on the other hand, if you do the midpoint rule, you can see again that there is this tendency of balancing errors, where if you looked especially at the rightmost of the rectangles, you have quite a bit where I'm tapping the board that's really not there under the curve, but you also have some up here that your rectangle misses that is under the curve. Well, it isn't clear just looking at my picture whether this thing is too big or too small or right on, but it would actually turn out to be a little bit on the big. And if you were to grind through the numbers. So you can't say for all cases either that the trapezoidal rule is low and the midpoint is high, or the other way around. It depends on the situation that you have. And in a typical situation, your curve will be concave up some of the interval and down some of the interval and so on. And so things would be difficult to predict without just simply working out all the numbers. But there is a tendency, certainly, when it's concave up and increasing, for the trapezoidal rule to overestimate and the midpoint rule to underestimate and the Simpson rule to be closer. You can certainly say those things as general statements. So let's look at the maple a little bit. The demand as far as employers for people that really can do numerical analysis. Do you need one short? Okay.
No.
You got enough? Okay. So if you bring up the package that says student and end it with a semicolon, you get to see all the different commands that are available. And if you notice in there is left box and left sum and middle box and middle sum and right box and right sum and Simpson, and there's also trapezoid, the very last of the commands. So it will do Simpson's rule or trapezoidal rule with the appropriate command, and it'll do the midpoint rule with your middle sum. So an example of where you would use computing in this sense in a practical way is the logarithm, because the integral of 1 over t, say t equals 1 to 2, you integrate 1 over t, you get log t, right? Log 2 minus log 1 gives you log 2, because log 1 is 0. So one way that you could build a table of logarithms is by doing numerical integration of the formula 1 over t from 1 to whatever number you want the log of. The integral 1 to 3 if you want log 3. Integral 1 to 4 if you want log 4. Okay, so if you type Simpson and your function and your limits, then the last number, the 4, that's how many slices. So that's your 5-point Simpson formula. You have 5 points, you have 4 slices. My picture here is the one I used for the trapezoidal rule, but it's the same 5 base points and so on. So what Maple wants you to say is how many slices, and then it figures how many base points it is. So if you do that, you get a formula 2, which is using the summations and so on. And if you do EVALF, you see 0.69325. Well, if you check your calculator for natural log 2, the first of those digits would be exact. It's the number that's 3 isn't exact for all the digits because you would need to take more slices or smaller spacing. But if you take 6 slices, Simpson 1 over t equals 1 to 2 and then 6. So you're taking a 7-point Simpson rule, and then your answer is number 5, 693169. If you ask what's log 2, EVALF log 2, numbers line 6, so you have 693147. So the 7-point Simpson rule got you log 2 correct to, the first 4 digits anyway. See, if you think about your curve, you have to take a smaller spacing to get a good value for log 2 because you're working with this part of the 1 over t curve where you have quite a bit of curvature. If you're looking at larger numbers out here, your 1 over t curve is much more nearly linear, and then you don't need as many slices in your Simpson rule or whatever rule you're using because you don't have so much curvature. Anyway, if you look on down the page, I have EVALF Simpson 1 over t from 1 to 2, 8 slices, so that's a 9-point Simpson rule. See, now I have 69315 and 54, say, compared with the exact 693,147. And then the next one, number 8, you see you're closing in on the exact value as you take more slices. For instance, the last 2 lines, I did the Simpson rule with 10 slices for log 3, number 9, and then asked for the exact value of that. And you see number 9, 109,866 and exact 109,8612. They're pretty close. So you can use numerical integration to produce a table of values of a function. People also can use infinite series, which is actually more efficient than Simpson's rule for this. And when we get to chapter 10, I'll show you how you do log 2 using an infinite series. But those are the two methods that are out there to get exact values for functions. So before you get away from me, there's some, I forgot last Thursday to bring the test, and I brought it Friday, but there's some of you here who didn't get the test last week. So if you need a test, put up your hand.